Good evening everyone. This is the 11th problem solving session for the NPTEL course IC Engines and Gas Turbines. So I am Anindo Dotto, a PhD candidate and a PMRA fellow from IIC Bangalore. So today is the last second last session, problem solving session for this course, and today we will be discussing questions and problems on the topics of radial inflow turbines, nozzles and intakes. Till now over the course we have seen the second part of the course. We have dealt with the gas turbine cycles, the thermodynamic analysis of the cycles, and then looked into different the two important components of the gas turbine based power plants or gas turbine based aircraft engine, which are different types of compressors and turbines. Now we will look at if we now consider the aircraft engine, the two extreme parts that are present in an aircraft engines are the intakes, which is also known as a diffuser, and the nozzle, so which ejects the exhaust jet at a very high velocity, and eventually we get thrust for the aircraft to fly, right? So we will be discussing those two parts in this in today's session, which nozzles and diffusers. And next week, which will be the last problem solving session, it will be a revision session where we will be solve problems from all the topics that have been covered in this course, both IC engines and gas turbines, and just do a recap of everything. Okay, so let's begin today's session on the topics of radial inflow turbine, nozzles and diffusers. Okay, so the first question for today is, which of the following is the correct, which is the correct order of flow for a 90-degree radial inflow turbine? Okay, so we have to choose the correct order in which the flow goes through in different parts of a radial turbine. Okay, so we know in a radial turbine the major components involve the volute, impeller, nozzle ring and an exhaust diffuser. Okay, so the options are: option A, first is inward flow volute, second is nozzle ring, third is impeller, fourth is exhaust diffuser. Option B, inward flow volute, impeller, nozzle ring and then diffuser. Option C, first nozzle ring, then impeller, then exhaust diffuser and then inward flow volute. And the option D is nozzle ring, inward flow volute, impeller and exhaust diffuser. So which is the correct answer for this one? Whoever are attending this can write your answers in the chat box. Sorry. So let me draw the schematic of an inward flow radial turbine. The flow direction in this case is just opposite to what we see in case of a centrifugal compressor basically. Okay, so let me draw this. So this is what we have, our impeller, okay. Schematic, okay. So this is our volute, okay. This part is our nozzle ring. So you have a annular region and blade space, as well as the spacing between the flow passage between each of these blades acts as a nozzle. Okay, then this is our impeller and this is our diffuser. Okay. So what happens is that in this case the flow direction is from this is our flow direction. Okay. So what happens? There is flow comes first through this volute, then passes through the nozzle ring, then then it enters the impeller. So the flow that is entering the impeller in general has a very high, the velocity has a very high tangential component, and then the impeller directs the flow, and the flow eventually comes out axially at the impeller outlet, and there is an exhaust diffuser there, so which basically a diffuser acts to reduce the velocity to a very low value. Okay, so this is as you can see, this is like opposite to what we have seen a centrifugal compressor. Okay, so the correct answer is option A. First we have inward flow volute, then nozzle ring, then impeller, and then exhaust diffuser. Okay, this is a schematic for radial turbine. Okay, and if you remember, so radial turbine, what we have is radial inlet, so flow enters radially and flow goes out axially. Okay, this is for radial turbine. And in case of an centrifugal compressor, you have seen the schematics looks like the same, but the flow enters axially and then goes through the impeller, and then after that there are diffuser. In that case we have diffuser ring at the outlet of the impeller, and then the volute. Okay, so that's the difference. Yeah, let's move on to question number 2. So question number 2 is, for a 90-degree inward flow radial turbine, which of the following is correct for the velocity triangle at impeller inlet? And given that the impeller inlet is denoted as suffix 1, that CR is the radial velocity component, CW is the wall velocity component, U is the blade velocity, V is the relative velocity, and C is the absolute velocity. Okay, so now if I just try to draw a schematic of this. Okay, so this is, let's say, our nozzle ring. So here you have static rings placed vanes placed like this. These are stator vanes. Okay, and fixed. Okay, after this you have the impeller. Okay, so impeller basically has this, it's saying that this is 90-degree inward flow radial turbine. If you remember this, in case of centrifugal pumps also, when we said that the vanes are 90-degree, with that means that the blades at the will be like this. So the inflow will be radial. Okay, so this is our impeller which is rotating in this direction. Okay, this is our impeller which is rotating in this direction. Okay, so this is our at the inlet to the impeller. If we draw the how the our velocity triangle will look, so you see this is at the nozzle ring blades are static, so CW will come in, sorry, the C1, the absolute velocity will be in this direction somehow. So this is our C1. Okay, and then this is our U1, the blade speed. Okay, and since the blade angle is 90 degree at the inlet, the relative velocity component will be like this, V1. Right, so this is how our velocity triangle at impeller inlet will look like. Velocity triangle at impeller inlet. Okay, so which is this region, this is our 1. Okay, so and you see there, so this is the radial direction, so CR1 equals to V1. Okay, and you can see this the wall component of velocity, which is the projection of C1 in the tangential direction, that is equals to CW1. Okay, so from this velocity triangle we can say that for this case option D is the correct answer. Okay, so CR1 equals to the radial component of velocity is equal to the relative velocity component, and the wall component of velocity is equal to the blade speed at impeller inlet. Okay. Yeah. So this is kind of similar to the velocity triangle is kind of similar to what we see in case of outlet of centrifugal compressor, just the directions are slightly reversed. Okay, so I guess this is clear. Let's move on to the next question, question 3. So question 3 is for a 90-degree inward flow radial turbine. That is the what we saw in the previous two questions. We had drawn the schematic and also seen the how the velocity triangle at impeller inlet looks like. The question is for how the flow through the nozzle ring leads to, the options are increase in total temperature, increase in total pressure, decrease in total pressure, and constancy in total pressure. Okay, so let's go back. So for a 90-degree radial turbine, this is our nozzle ring. So nozzle ring is placed upstream of the impeller. Okay, so through all the discussions that we have done on turbines and nozzle rings, on turbines and compressor, we have seen that nozzles and diffuser are basically there is no work or heat interaction happening in nozzles and diffusers, right? So total temperature remains constant because of no work or heat interaction, right? Now, so the option A is not correct, because increase in total temperature can happen only if there is some heat addition or work input to the system, but in the nozzle ring no such interaction happens. Next is increase in total pressure. Again, since there is no work input, the total pressure will also won't change. Now if the flow is isentropic through the nozzle ring, then the total pressure will stay constant, right? If flow is isentropic, then total pressure will stay constant. Okay, but since in practical cases the total pressure the flow is not isentropic, there are flow irreversibilities involved, there will be an increase in entropy, and as a result of which the total pressure actually decrease. Okay, practical flows are non-isentropic, right? So that's why total pressure decreases. Okay, so the correct option is for this will be option C. Okay, so let's also just, this is the TS diagram for the radial flow turbine. In the lectures this TS diagram for the compressors have been discussed in detail. This is for the turbine. Okay, and different stages. Okay, so this figure is taken from the book by Gas Turbine Theory by Saravanamoto et al. Okay, Saravanamoto is the main author. Okay, also some of the lecture contents discussed by the professor is from this book, so you can refer to this book also if you want to learn more about these things. Okay, so let me just briefly go through this TS diagram once. So this is the schematic on this figure 7.5. So state 1 is like, so first we have nozzle vanes. So 1 is the inlet to the nozzle vanes, 2 is the exit to the nozzle vanes and inlet to the impeller, 3 is the exit of the impeller or rotor. Okay, and 4 is the exit from the diffuser. Okay, so now if you see on this TS diagram, this state 1, state point 1 and state point 2. Okay, so here in this case you can see this process is non-isentropic. Okay, so the flow through the nozzle vanes is non-isentropic. Okay, so so if you at state point 1, if you add the corresponding velocity square by 2 cp c1 square, we get this state point 01. So this is basically our T01. Okay, and T01 is equal to T02 because there is no work or heat interaction happening. Okay, and now you see, so from one it, and the state point 2 is the exit from the nozzle, and there is, as you can see, the process is not isentropic because the process curve is not vertical, it's inclined, so there is an increase in entropy happening. And and if you go, and this difference between 0 2 and 0 2 state point, this is the velocity rise, this is the corresponding what we call the velocity temperature, because C2 square by 2 Cp. Okay, and you can see this, if and here, like if you draw a pressure isocontour through 02, we get P02, and P02 is less than P01. That is, there is a fall in stagnation pressure happening when there is flow through the nozzle, right? So this is similar, if you remember, this part is similar to what we have seen in also in case of diffusers and TS diagram for our diffuser of a centrifugal compressor, right? There also we will see the total temperature stays constant, but there is a fall in total pressure happening due to flow irreversibilities. Okay, and then 2 to 3 is our and also one more thing, the velocity at the velocity at nozzle outlet C2 is higher than C1, because as we know, in the nozzle the static pressure rises, which we can also see that P2 is less than P1, and velocity, and with a corresponding rise in kinetic energy or velocity, right? So C1 is, C2 is greater than C1. Okay, and then 2 to 3 is our rotor, where there is work output happening, as a result of which the total temperature is falling. Okay, so here T03 is, here it is T03, you can see T03 has fallen. Okay, and then compared to T02, so this is our T03, and this difference is basically our Cp times this difference is basically our work output. Okay, right, this is delta T0, so this, if you multiply this with Cp, we will get the work output. Okay, and then 3 to 4 is a small part because there is a diffuser again, so there is a small rise in static pressure. Okay, and also, as you can see that the velocity decreases. Okay, so yeah, any questions? So this is a very brief, so I had 3 questions and a small additional discussion on radial inflow turbines. Okay, you can refer to this book anytime, and for additional details, like not only on for this topic, all the other topics, because much of the lecture contents had been covered from this book. Okay, so let's move on. Question 4. So now we'll look into questions on nozzles and diffusers. Okay, so the first question on those topics is, for incompressible flow through diffuser, the options are: pressure always rises but velocity remains constant. Option B, pressure decreases when the inlet flow is supersonic. Option C, velocity always decreases and pressure increases. And option D, velocity increases when the inlet flow is subsonic. So which is the correct answer? You can type in the option in the chat box. Yeah, right. Correct answer is option C. So velocity always decreases and pressure increases. So this is the fundamental idea, or say working principle of diffuser. That is to reduce the in any diffuser, whether it's the flow is incompressible, compressible, subsonic or sonic, subsonic or supersonic, the velocity will always decrease at the outlet of the diffuser with a corresponding rise in pressure. Okay, and for the nozzle it's opposite, velocity will always increase with a corresponding decrease in pressure. Okay, so We're going to the next one, question 5. Which is the correct for fluid flow through a diverging passage? Options are: always behaves as diffuser. Option B, always behaves as nozzle if the inlet flow is subsonic. Always acts as diffuser if the inlet flow is supersonic. Option D, it can act as both nozzle and diffuser. It depends on the inlet Mach number. Yeah, the correct answer is option D. So what is seeing is that we have a diverging passage. Okay. So based on the Mach number of the flow, inlet Mach number of the flow, that is whether the inlet flow is supersonic or subsonic, based on that it can act as either nozzle and diffuser. Okay. So for that we have this area velocity Mach number relation, which is dA by A. So dA is a change in area, equals to m square minus 1 into dV by V. Okay. So for a diverging passage like the one shown this diagram, right, what is dA? dA is positive or negative? dA is positive, right, because the area is increasing as the flow passes through the diffuser, right? That's why if let's say so let's say if this is means diverging passage. So case A, if Mach number is less than 1, that is flow is subsonic. Okay. So then what, m square minus 1, this term is negative. So since the left hand side dA is positive, on the right hand side there are two terms, m square minus 1 and dV. So m square minus 1 is negative, which implies that dV also has to be negative, which means that velocity is decreasing. Okay. So it means that when we have a subsonic inflow, then in a diverging passage this will act as a diffuser. Okay. So this will, if with the inflow the Mach number is less than 1, this will act as a subsonic diffuser. Okay. Now let's consider the case B. So again dA is greater than 0 because we have a diverging passage. Now let's say the inflow Mach number is greater than 1, then which is the flow is supersonic, then m square minus 1, this term is positive, right? So again going by that area velocity Mach number relation, m square left hand side is positive, dA is positive, so m square minus 1 is positive, so dV also has to be positive, which means that velocity is increasing. Okay, which means that it is acting as a nozzle. Okay, so when we have a supersonic inflow, a diverging passage acts as a nozzle, right? So that's why this explains the answer that a diverging passage can act as both nozzle and diffuser based on the inlet Mach number. For a supersonic inflow, a diverging duct will act as a nozzle. For a subsonic inflow, a diverging duct will act as a diffuser. Okay, and the case is vice versa if we consider a converging area duct. Okay, so moving on, in the question 6, for supersonic flow through the nozzle, the pressure, you have to fill in the blanks, what happens to the pressure and velocity while flowing through it. We'll wait for one of you to answer this question. Just think again. It's nozzle. nothing to do is what happens in a nozzle. So again this is thing. So the fundamental principle is of nozzle is pressure will decrease and velocity will increase. Okay, whatever be the flow, whether the flow is supersonic or subsonic, whenever a nozzle means, while the pressure will decrease and velocity will increase. Okay, and again just I want to repeat, for diffuser pressure will increase and velocity will decrease. Okay, so this pressure is static pressure. Remember, this is static pressure. We are not talking about stagnation quantities here. Static pressure will increase in a diffuser and velocity will increase. No, what I said, just nozzle does not means that the area will decrease. Okay, for nozzle just remember this is the fundamental working principle. Okay, I am coming to supersonic flow part then. So this is so in diffuser this is in nozzle pressure decreases, velocity increases. In nozzle pressure decreases, velocity increases. In diffuser pressure increases, velocity decreases. Okay, now depending on what kind of flow it is, we might need a whether the flow area will increase or decrease, that depends on, that is given by this area velocity Mach number relation. Okay, so for, let's say, if I refer to this area velocity Mach number relation, for nozzle what is the requirement? Our velocity is increasing, right? So dV is positive, right? So dV is positive. Now when we have supersonic flow, this m is greater than 1, so m square minus 1 is greater than 1. So our right hand side is positive, so left hand side also has to be positive, so dA is greater than 1, right? So for supersonic nozzle will look like this. Okay, yeah, right, this is what I also discussed in the last question, right? So just be clear about this, just clearly remember this is the basic working principle of nozzle and diffuser. Now how, just don't assume that since it is a converging area duct it's always a nozzle, or if it's a diverging area duct it is the diffuser. This is because we are mostly the flows that we encountered or have studied mostly those are subsonic, so that's how we are used to think. But when the flow becomes supersonic, the case is reverse. Okay, so we have to careful about, like, just be careful of the kind of flow and this, and the fundamental principle is like this. Okay, so moving on, question 7. Function of an intake of aircraft engine is to, the options are: increase the kinetic head of air at the entry of the engine, option B, increase the pressure head of the air at the entry of the engine, option C, reduce the heat losses, option D, increase turbine work output. Correct answer is option B. Okay, so this is, so what we have, this is, let's say, our intake duct, and after that what we have is our compressor, like just a rough sketch I'm doing. Okay, so what happens, in intake duct acts as a diffuser, right? So as I just go back to the previous slide, as I said, diffuser means the pressure increases and velocity decreases. Okay, so as you know that in a, as I've said, commercial aircraft that flies at very high speed, so which is at around the flow Mach number is around close to 0.8. Okay, so what happens in a diffuser intake duct is the flow enters, right? So after that the flow decelerates to a low velocity, and there is a corresponding rise in pressure at the intake of at the entry to the compressor. Okay, so that has two benefits, so that we get slightly higher, so we get slightly the pressure head of the flow is increased, and again the velocity decreases. Okay, so if the velocity decreases, that is also beneficial, because if you remember the expression for pressure rise to a compressor, that depends on the flow velocity. Now if the flow velocity is too high at the intake of the compressor blades, the relative velocity component will also might get high, and if the Mach number based on the relative velocity component goes beyond 0.8, there the shocks can form on the compressor blades, and then there will be much more losses, and the compressor won't work efficiently. Okay, so for that reason it is also useful to that the inflow velocity to a compressor is reduced to some permissible value before entry to the compressor, so that the compressor can work efficiently. Okay, and handle all the stresses and minimal losses, right? Okay, any questions so far? Okay, let's move on. Okay, so question 8, select the correct sentence from the following. Sorry, this is a typo. Yeah, okay, so the flow, yeah, I will let you guys read the options correctly, just read them carefully, and just tell me, just type in which you think is the correct answer. This is again similar thing, nozzles and diffuser. You have to just keep in mind of the basic working principle of a nozzle and diffuser, and also keep in mind of that area Mach number relation, which is dA by A equals to m square minus 1 equals to dV by V. Okay, so this is a very important relation. Yeah, right, B is the correct answer. So let's say the fluid pressure along the length of the ducts increases for subsonic inlet through a diverging duct. Okay, so a diverging duct means dA greater than 0 given subsonic inlet, which means Mach number is less than 1, right, which means dV is also less than 1, right? So basically subsonic, we are talking about a subsonic diffuser. So subsonic diffuser means velocity is decreasing, right? So which means pressure will increase. Yeah, so the correct answer is option B. Now if you can go over the other option, you will see there is some contradiction happening, and you will find out that the other options are not correct. Okay, okay. So, and you can explain the that using this area velocity Mach number relation and the basic working principle of nozzle and diffuser. Okay, okay, let's move on to the next question. In case of scramjet engine, air enters from intake at dash speed and encounters combustion at dash speed in the combustion chamber. So again you can type in the option. Yeah, option A is the correct one. So two things. So ramjets and scramjets. How is this? How, first of all, just ask me a question. How is ramjets and scramjets different from other air breathing engines like let's say turbojets or turbofan engines. Any one of you can unmute and say how ramjets and scramjets are different from let's say turbojet or turbofan engines. Ramjets and scramjets, right, they have no rotating parts.
They have lower efficiency and they can fly higher altitudes.
No, that is not the basic difference. That is coming to the, but the main difference is that they don't have any rotating parts. Yeah, that is also one difference. But the major thing is that they turbojets and turbofan, you will find that mostly they fly in subsonic speeds, Mach number less than 1. Ramjets and scramjets operate at flight speed which are supersonic, and they don't have any rotating parts, which means that in turbojets and turbofans we have compressors and turbines, which are turbo machines, right? And there is mechanical compression of air, as after it goes, the air goes inside the engine through the intake. But in ramjets and scramjet, they don't have any, the compression that we get is based on the ram effect, which is basically the thermodynamic compression. Using, we have shock systems and ram effect, which we use to achieve the compression. Okay, so for ramjets and scramjets happen as supersonic speed. Okay, this is also supersonic flight speed. This is also supersonic flight speed, supersonic. Okay, but in ramjet the combustion happens is a subsonic speed. Okay, so what happens is that the flight velocity is subsonic, supersonic, which means flow is entering through the into the engine at supersonic speed. But after that, the air compresses, its pressure, its velocity reduces, and the flow becomes subsonic. Okay, when it goes through the combustion chamber. Okay, so the in the combustion chamber of a ramjet engine, the flow is subsonic. Okay, but in in scramjet, which is also sometimes known as supersonic ramjet. So scramjets, the flight speed is like also higher than ramjets, which can go to hypersonic flight speeds. So what happens in scramjets, the flow velocity after it undergoes compression in the engine still remains supersonic when it is going to the combustion chamber. As a result of which the combustion is happening also at supersonic speed. Okay, so this is the difference between ramjet and scramjet. That in ramjet we have the combustion chamber, the flow is subsonic, and in scramjet the flow is still supersonic. Okay, so to repeat again, that in ramjet at the inflow of the engine the flow is supersonic, but it becomes subsonic when it reaches the combustion chamber. But in scramjet, flow is supersonic, but like what to say, the Mach number is much higher than what we experience in ramjet. So the flow velocity reduces to a lower supersonic value, and then combustion happens in the combustion chamber. Okay, all right. Any doubt?
Sir, why is it so?
Okay, so why is it so is that is again the how the working principle is. So ramjets, okay, so ramjet you will see that the Mach number of operation is generally under Mach 2. Okay, and then at the inflow in both scramjets and ramjets, at the inflow we get a system of shocks, okay, that basically compresses the air. All right. So and in scramjets the flight speed is still higher, like the at the inflow the Mach number is generally greater than 0.2, while in ramjet it might be less, it's mostly less than 0.2, sorry, less than 2, not 0.2. so let's say this is like inflow Mach number is, this is greater than 2. Okay. So this in ramjets, if you look of any book on aircraft propulsion, you'll see in ramjet the shocks, after the shock system we get a normal shock. Okay. Now in when the flow undergoes a normal shock, the flow becomes subsonic after the normal shock. But in scramjet mostly we get a system of oblique shocks, and again and after the oblique shock generally the flow still remains supersonic, but the flow Mach number reduces. Okay, so this has to relate, this has to do with the how the system of, what is the system of shocks that we get in ramjets and scramjets. Okay, like for this we have to study, like look into more into this, how one some gas dynamics textbooks on compressible flows. Okay, but to, let's say if I explain, try to explain in simple term, you would see this in ramjets the inflow Mach number is supersonic, but it is what to say, maybe lower supersonic, it is more closer to 1, but in scramjets the inflow Mach number is much higher. Okay, so the flow velocity, like when the it is undergoing compression, the flow velocity is reducing. Okay, so in ramjet that flow velocity reduces below 1, so the flow becomes subsonic. But in scramjet, the as it goes through that oblique shock system, the flow velocity reduces, but it does not go lower than 1, it still says higher than 1. Okay, so that's why we get like the in the combustion chamber the flow is still supersonic and we get supersonic combustion. Okay, like supersonic combustion is very difficult to handle, and many complexities are also associated with this, but that comes with the cost of getting that hypersonic flight speeds. Okay, does that answer your question?
Yes, sir. Yes, sir.
Yeah. Okay. Yeah, but
Sir, one more question.
yeah, go ahead.
Sir, why that supersonic planes get socks? Socks, sir.
Because we get
Socks.
shocks. Okay,
Yeah.
you don't, you haven't, didn't have you have, do you have you taken any course on, let's say, gas dynamics or compressible flows?
No, sir.
Okay, so what is what is Mach number greater than 1? So so do you know what happens in a shock? So let's say upstream of the shock the flow Mach number is, just I'm talking about a normal shock like this. Okay, let's say, so upstream of the shock, this is the, let's say, flow direction. Upstream of the shock the Mach number is greater than 1, and downstream of the shock Mach number is less than 1. Okay, this is how, and this shock is a very thin region across which there is a sudden jump happens. Okay, so what is Mach number greater than 1? What does that mean? So Mach number greater than 1 means that the flow velocity is higher than the speed of sound, right?
Yes, sir.
Right. So so the, if you know that there is always some, the in the flow the information is communicated in terms of pressure waves, and these pressure waves generally travel at the speed of sound. Okay, all right. So now when there is this flow velocity is greater than 1, sorry, greater than the speed of sound, right? So the, since the pressure waves are traveling at a lower speed than the flow velocity, all the information doesn't get communicated throughout the flow. That's why we get like a shock. Let's say if I give you an example, this, yeah, let's say we have something like a body like this. this, let's say here the flow is subsonic. Okay, let's say we there is some reservoir here and we start the flow. Okay, so if we'll see that what happens if the inflow Mach number is like this, subsonic. So when the flow will start, it will come here. So there is some like so there is some obstruction in the flow, right? So this the idea that this obstruction is present is communicated to upstream of communicated upstream by means of pressure wave. So finally the flow streamlines look like this, right? This is, I guess all of you know this about this, right? The flow will look like this, right? Now let's say again, if you have a inflow Mach number which is greater than 1, what happens is that the flow is now the flow velocity is much higher than the speed of sound. Okay, so let's say one fluid particle comes, okay, and hits here. So that generates some pressure waves. So some pressure wave will generate and move upstream to communicate the flow that this obstruction is present, right? But since the flow velocity is the flow velocity is higher than this pressure wave velocity, right? So the pressure wave cannot communicate the information throughout upstream of the flow that that some obstruction is present. As a result of which, what happens is in kind of flow that will get a shock like this. Okay, so this is now Mach number is greater than 1 here. So downstream of the shock, Mach number becomes less than 1, and here again the flow will go like this. Okay, this is basically why we get shocks. Like this is just a simple example I gave you, but again, like if you want to know more about the shock systems and all, you have to study some textbooks on gas dynamics. Okay, does that answer your question, Shubham?
Sir, yes, sir. Yes, sir.
Okay, yeah.
Thank you,
So
sir.
this is the basic idea. Yeah. So yeah, so this can be also explained in detail using like saying about the thermodynamics and why pressure waves propagate and everything. Okay, but you can read about it. Okay, let's move on to the next question. So for a given reservoir temperature and pressure, the flow at the exit of a choked convergent divergent nozzle should be. So what is a convergent divergent nozzle? So we have a converging part, then a throat, and then a diverging part, right? This is how a CD nozzle looks like. We call a CD nozzle. Okay, yeah, right. So this is CD nozzle. So flow here is less than 1. So this is throat. Here the flow is sonic, and and then the flow becomes supersonic. Okay, so this is again like you can explain it from remember the area velocity Mach number expression. So why like a diverging passage will act as a supersonic nozzle, right? So at the exit, so flow is choked means at the throat Mach number will be equal to 1. Okay, and so at the exit the flow will become supersonic. Okay, moving on. Question 11. For flow through nozzle is said to be under expanded when the nozzle exit pressure is, options are higher than ambient pressure, equal to ambient pressure, equal to reservoir pressure, lower than ambient pressure. It says under expanded. What is under expanded? So we have we have a CD nozzle like this. This is the pressure at ambient. Okay, so under expand, so what is, and let's say this is the exit pressure P. So what is perfectly expanded? So this is Pi. So this is true, right? Pi is always higher than P, right? Because this is a nozzle. So in nozzle there will be drop in pressure and rise in velocity, right? So inlet pressure is higher than the exit pressure. So in perfectly expanded nozzle, P exit pressure will be equal to the ambient pressure. Okay. So when we mean under expanded, this means that in the nozzle the expansion has not been completed, so that is under expanded, which means that PE is higher than PA. And over expanded means that it has expanded more than what is the ideal case, that is PE is less than PA. Okay. So to repeat once again, expansion in a nozzle means the pressure is decreasing, static pressure is decreasing. So in perfectly expanded state, the exit pressure, nozzle exit pressure will be equal to ambient pressure. In under expanded state, it means that the flow didn't expand fully, so P is still higher than PA. And over expanded means it has undergone expansion more than the ideal case, so that is P is less than PA. So under expanded is option A. Okay. So based on this is like, if you are interested, you can search over expanded and under expanded jet shock structure. So if you are interested to know, you will see that in under expanded and over expanded jet, we get a very interesting shock structure at the exit of the nozzle, and those two shock structures are very different. Okay, and like we will get some shock triangles and very interesting stuff. You can Google this and see the images that are taken experimentally and how it looks like. Okay, and all this, like why those structure forms, and and how why though there's a different in over expanded and under expanded case, that you can will be able to explain if you do a course on gas dynamics. Okay, but for your this is something interesting, you can look this up. So when this you under expanded and over expanded jets, these kind of jets you get in case of this hypersonic or supersonic flights, because the flight is supersonic, the also the flow coming, we generally have a CD nozzle, and the flow coming out of the nozzle is also supersonic. So and based on the ambient pressure, it can be either over expanded or under expanded, and you get this kind of interesting shock structure at the exit of the nozzle. Okay, all right, so let's move on. Now question 12, this I already have discussed, which is correct about the ramjet engine. So any of you just tell me the correct option. This is about the aircraft speed and the combustion. So air, yeah, right, option C, air enters the engine in supersonic speed and encounter subsonic combustion. Okay, now question 13, this is a small numerical that I have to solve. So choose the correct relation between stagnation pressure and static temperature for isentropic flow through the nozzle at sonic exit condition. Okay, so what is this is, so let's say I have a nozzle. So it's saying that at exit the flow is sonic, which means Mach number is equal to 1, which that means that the flow that is coming inside the nozzle, that is subsonic, which means that we need a converging area duct. Okay, so that's why I'm drawing a converging area duct here. Let's say this is state 1 and this is state 2. Okay, so as it's a nozzle, the stagnation temperature remains constant, right? So T01 is the stagnation temperature at the inlet, equals to T02, and let's say denote it as T0. So stagnation temperature is constant throughout the nozzle because there is no heat and work interaction. Okay, so now let me write the energy balance. So enthalpy plus velocity at inflow equals to enthalpy plus velocity at outflow, right? Okay, so this H1 we can write as, so this is basically our stagnation enthalpy, so we can write H01 equals to H2 plus C2 square by 2. Now H01 is CPT01, H2 is CPT2, and this is C2 square by 2 velocity. Okay, now I divide both side by Cp, and T01 is what I wrote as T0, stagnation temperature is same, so this is Cp, sorry, T2 plus C2 square by 2 Cp, right? Now what is written is that the exit condition is sonic, which means C2 is equal to the speed of sound, right? Because Mach number is 1, so the velocity at the exit of the nozzle is 1, sonic. Now what is the speed expression for the velocity of sound? That is square root of gamma r T2, right? So we put that here, T2 plus C2 square means gamma r T2 by 2 Cp. Okay, now what we can write Cp in terms of r and gamma. So what is Cp? Gamma r by gamma plus 1, right? So now if we take T2, sorry, gamma r by gamma minus 1. So if we now take T2 common, what we'll get? This is 1 plus gamma minus 1 by 2, or we will get T0 by T2 as gamma plus 1 by 2. Okay, so the correct answer is option A. Okay, so what does this tell is that this is like if at the exit of the nozzle, right, this is if nozzle exit flow is sonic, then the static temperature to the stagnation temperature to static temperature ratio is given by this. Okay, and this is also called critical temperature ratio. Okay, this is and also this condition is called that the nozzle is choked. Okay, so this is condition of the nozzle choking, because the at the exit of the nozzle the flow velocity is reached Mach number 1. Now for this nozzle we can't have higher velocity, right? Because if we want to have velocity higher than this, the flow has to become supersonic, and we know that a converging duct doesn't act as a supersonic nozzle, right? So this is the case where at which the maximum flow is going through the nozzle, and which means that the nozzle is choked, and this is what we call is the critical temperature ratio at the nozzle exit. Okay, now just want to add one more thing, sorry, that is what we call is the critical pressure ratio. This is which is the, so I had this nozzle, right, let's say 1, and this is 2, right, and let's say this nozzle has an isentropic efficiency of eta n. So the definition of nozzle isentropic efficiency was discussed in this week's lecture, right? So if this is given, then P01 by P2, this is what we call the critical pressure ratio, which means that let's say critical condition comes when, which means that the flow at 2 is sonic. This is what we call the critical condition for a nozzle. Okay, in that case, this is the critical pressure ratio is given by this 1 minus eta n gamma minus 1 by gamma plus 1 whole to the power gamma by gamma minus 1. Okay, this is just for information. Just you can see the derivation in the book by Saravan Nomotu, the one that I said. But yeah, I will, so at the end of today's session I will solve a problem on aircraft engine propulsion cycle, because now you know how to deal with each and every component. Okay, then in that case this expression will be useful. Okay. So just to repeat, the critical condition means that at the exit of the nozzle we have the nozzle is choked, and at the exit of the nozzle the flow velocity is equal to the speed of sound. Okay, in that case the critical pressure ratio is given by this. Okay, and the critical temperature ratio is given by this T0 1 by T2 equals to gamma plus 1 by gamma plus 1 by 2. Okay, all right. Second, let me check one more thing. Yeah. Okay. Okay. Any questions? Okay, so yeah, I guess this is the last MCQ for the day. Then we'll move on to some numericals. So purpose of any aircraft gas turbine inlet is to provide, the options are supply air, sufficient air supply to the compressor, have a minimum drag force, reduction in velocity, option D, all of the above. This is the correct answer. Yeah, D, right. So these are all at the like this all should be accomplished, all these factors should be accomplished by an aircraft engine inlet. Sufficient air supply to compressor, minimum drag force. So minimizing the drag force is important for each and every component of aircraft engine, because drag force is basically an opposing force to thrust, which and opposing or retarding force to the which acts in direction opposite to the in aircraft flight. And reduction in velocity is important, as I tell you, because so that the compressor can work efficiently, right? Okay. So question 15, these are numerical on nozzle to illustrate the idea of nozzle isentropic efficiency. So let's look at this. So air at 250 kPa and 950 Kelvin enters an adiabatic nozzle. So adiabatic nozzle means there is no heat loss, and in a nozzle there is no work input or output, which means our stagnation temperature or stagnation enthalpy will be constant at low velocity and discharged to a pressure of 80 kilopascal. If the isentropic efficiency is 92%, determine the maximum possible exit velocity, exit temperature, and the actual exit velocity of air. Okay, assume constant specific feed for air, which is Cp is equal to 1005 joule per kg Kelvin. Okay, so let me draw the schematic. Right, so P1 is equal to 200 kilopascal, T1 is equal to 980 Kelvin, and it's saying that these are low velocity, which means that the inlet velocity is approximately equal to 0. So if the inlet velocity is approximately equal to 0, the stagnation temperature and pressure is equal to static temperature and pressure, right? Because you know that in stagnation temperature the term comes like static temperature plus c square by 2 Cp. Now if the velocity is very small, stagnation temperature is equal to static temperature. Okay, so now let me draw the TS diagram. So this is our P1 line, this is our P2 line. Okay, so now the flow is going from somewhere from here to here, right? Now if the flow would have gone from here to, let's say, 2s, right? So the first question is the maximum possible exit velocity. So we can attain the maximum possible exit velocity at the nozzle, at the end, at the exit of the nozzle, when the flow is isentropic, right? Which means that it follows this curve from 1 to 2s, right? So 1 to 2s is the flow is isentropic, and this will give maximum nozzle exit velocity. Okay, so how to find that out? So this is our H1 plus C1 square by 2 equals to H2 plus C2 square by 2, right? This is our energy balance equation. Let's say I'm adding, sorry, H2s and C2s, because this is the, at the, in this case we are considering the flow is isentropic. Okay, now C1 square is approximately equal to 0, so this is H1 equals to H2s plus C2s square by 2, which is C2s is 2 times square root of 2 times H1 minus H2s. Now if we are in constant speed, it is 2 Cp times T1 minus T2s. So on the right hand side we know Cp and T1, we need to find T2s, which is the temperature at the end of exit of the nozzle if the flow is isentropic. So this we can find out by applying the isentropic relation, right? Gamma minus 1 by gamma. So this is P2 is 80, P1 is 200, gamma is 1.4, 1.4 minus 1 by 1.4, right? So T2s is 950 times 80 by 200, 1.4 minus 1.4, 1.4. So we'll get T2s as 731.2 Kelvin. Okay, so now if we put this here, C2s will be square root of 2 times 1005 into 950 minus 731.2. so C2s will come out as 663.2 meter per second. Okay, so this is the maximum possible exit velocity. Okay, so if the flow is isentropic, so what we did in this case, we applied the energy balance equation, or what we call the steady state steady flow energy equation from the first law of thermodynamics, and then assuming that the flow is isentropic, we computed what is the temperature at the end of the exit of the nozzle, and then we can put in the values and we are able to find out the nozzle exit velocity, maximum possible. Okay, so second part of the question is we have to find the exit temperature. Okay, so this time this is the actual exit temperature. Okay, so now we will use the definition of nozzle isentropic efficiency. So nozzle isentropic efficiency, what is the definition? Actual rise in kinetic energy divided by isentropic rise in kinetic energy, right? So what is the actual rise in kinetic energy? That is our equals to H1 minus H2, right? So if we come back here and look into this expression, right? So what is the rise in kinetic energy here? Just the difference in enthalpies, right? C2s by 2, this is our rise in kinetic energy, because the initial kinetic energy is 0, so that is the difference in enthalpy. So actual rise is H1 minus H2, and the isentropic rise is H1 minus H2s. So now if we, since the Cp is constant, this we can express in terms of temperature difference, T1 minus T2s. So eta n is 0.92, this is equals to 950 minus T2 by 950 minus T2s is 731.2, so we will get T2 as 748 Kelvin, right? So we see that the for non-isentropic flow, the temperature is at the exit of the nozzle is slightly higher, right? Nozzle exit temperature is higher than isentropic case. Okay, this is because of the flow irreversibilities. So because of, we can see that because of flow irreversibilities, we are not able to achieve the lower temperature and higher velocity. We will see that also the final velocity at the exit of the nozzle is lower. Okay, because of the flow, we are getting this because of the flow irreversibilities, and because of the flow viscosity and other factors, the flow is getting slightly heated up compared to the non-isentropic case. Okay, so option C is like last option. What is the actual exit velocity? So again, the what is the actual, this will be C2 equals to 2 times H1 minus H2, right? The 2 times the enthalpy, or 2 times Cp T1 minus T2. So this is 2 times 1005, T1 is 950, T2 we computed as 748, so we will get C2 as 637 meter per second. So this is, remember, this is lesser than in the ideal non-isentropic case. Sorry, in the isentropic case we are getting 633.2 meter per second, but in the actual practical case, this is less than C2s. Okay, which means that we are like, the idea of the nozzle is to eject the gases at the highest velocity possible, because if the exit the higher the exit velocity, the higher will be the thrust, but because of irreversibility is present in the nozzle, we are not able to achieve that maximum exit velocity. Okay, so any doubt so far? Okay, I guess this is clear then. Okay, so last problem for today, this will be a big problem. So till now we have, this is a problem on a turbojet engine cycle. So till now we have done thermodynamic analysis of mostly gas turbine power plants only, right? Now, and with isentropic efficiencies of compressors and turbines. But in this lecture we have also know how to define the do analysis of the two other components which are just specific to aircraft engines, that are the intake diffuser and the nozzle, and we have seen how to define the isentropic efficiency of those parts. Okay, and over the last two lectures we have been also got acquainted with the idea of the stagnation temperatures and how to draw a TS diagram with stagnation temperature and interpret the data from that, the how work is defined based on the proportional to the stagnation temperature deferments and all those things. Okay, so today let's do a full thermodynamic analysis of a turbojet engine cycle, okay, with all irreversibilities and everything involved. Okay, so let's go through the problem first. So we have a turbojet engine flying at a speed corresponding to Mach number of 0.7 and altitude of 8000 meter. Okay, so First is given is the compressor pressure ratio. So this is what is the pressure rise across the compressor. So the pressure at the exit of the compressor divided by the pressure at the inlet of the compressor. So this is Rp. Then we have turbine inlet temperature. Okay, first let's draw the TS diagram, then it will be okay. So as I had told in one of my earlier sessions, that in case of turbojet engine cycle we draw TS diagram in terms of mostly stagnation quantities. Okay, so because the flow velocity is significant, so that makes sense in this case, unlike in case of mostly in the thermodynamic problems that we did for gas turbine based power plants. We used to draw TS diagrams and express the work done in terms of the difference in static temperature only, because in those cases it is the baseline assumption that the flow velocities are very small, but that is not the case in case of aircraft engine cycle, because the flow velocity is quite significant and the stagnation quantities are quite higher than the static quantities. Okay, so first we have state 1. So this is, let's say, our P01. Okay, so let's all, okay, we'll write in like this way, 01 only, because they are stagnation quantities. So then this is our P02 and this is our 02 again. So this is our compressor. Okay, now you will see in the problem that there is a loss in pressure also happening in the combustion chamber. This we have dealt with also before in one of our problems, that the pressure, the ideal assumption is there is a constant pressure heat addition, but there is sometimes there is a loss in pressure in the combustion chamber that happens, as a result of which we draw another, let's say, line here. So this is our 03 and this is P03, and this difference is our delta PCC, the pressure loss in the combustion chamber. Okay, then we have, then there you have turbine. So this is our combustion chamber, then we have turbine. So this is 04 and this is our P04. So this is our turbine 03 to 04. Okay, and after that we have, these are P5 static pressure, this is our nozzle. Okay, clear? Okay, so on sometimes you also can draw this is our ambient pressure. So from ambient pressure to nozzle, so this is the state points are, 1 is our compressor inlet, 2 is our compressor exit or combustion chamber inlet, 3 is our combustion chamber exit or turbine inlet, 4 is turbine exit or nozzle inlet, and 5 is nozzle exit. Okay, so like just note that here in the, for the nozzle I have drawn the state point from stagnation pressure level to static pressure level at P5. So this you can relate if you go back to and check the this last week's lecture, where isentropic efficiency of nozzle was discussed, where we like how we can draw from its, so basically it's getting expanded to the ambient pressure level, which is P5. Okay, so let's write the, let's now referring to this TS diagram, let's see what is given data. So turbine inlet temperature will be T03, isentropic efficiency of compressor, that is eta C, isentropic efficiency of turbine, that is eta T, isentropic efficiency of inlet intake, which is, let's say, defined eta I, isentropic efficiency of the nozzle eta N, mechanical transmission efficiency is eta M. So mechanical transmission efficiency is that, so again just to in this case, in case of a aircraft engine cycle, the turbine work is just sufficient to run the compressor, there is no additional work produced. Okay, and but the turbine work will be slightly higher than the compressor work, because some part of it is lost due to mechanical friction associated with the shaft. So that is what is quantified using the mechanical transmission efficiency. Okay, Then we have combustion efficiency. We will see what is combustion efficiency in the when we will solve the problem. Then there is combustion pressure loss, which is 4% of combustion delivery pressure, which means that delta PCC, the pressure loss in the combustion chamber, is 4% of the combustion delivery pressure, which is means that the pressure at which the flow enters the combustion chamber, which is P02. Okay. Now we have theoretical air fuel ratio, A by F theoretical, which is 0.0194. Then we have given universal gas constant. So at given that the flight is flying at an altitude of 8000 meter, so in that case the ambient conditions, the pressure and temperature are given and the speed of sound are given, and again we have been given the specific heat and specific heat ratio values for air and gas. So in the compressor we will in the compressor the working fluid will be air, so you have to use the Cp and gamma values of air, and in the turbine and nozzle the working fluid will be the exhaust gas, for which the specific heat, let's say we give a CPG, that is 1147 joule per kg Kelvin, and this is gamma G, which is 1.333. okay. Is the problem definition clear? Any questions in any part? Then we can move on to the solution. Okay. Okay, let's start then. Okay, so first question is real total temperature at the outlet of the compressor, which means the total temperature at the outlet of the compressor, which means that we have to find out T02. Okay. Okay, so first we have to find T01. Okay, so T01 is our ambient temperature TA plus Ca square by 2 Cp. Okay. So Ca is our flight speed. Okay, so the static temperature at the inlet of the ambient condition plus the speed of sound, that will give us the total temperature at the inlet of the compressor, right? Okay, now what is Ca? Ca is given that the flight Mach number is 0.7 and the speed of sound at that altitude is 308.1. okay, so this will be equal to our Mach number times the speed of sound, which is 0.7 times the 308.1 meter per second. Okay, so now if you put in the values here, second, we'll get Ca as 215.67 meter per second. So T01 will be, we will get 259.34 Kelvin. Okay, so now we know what is the stagnation temperature at the inlet of the compressor. Okay, now next part is to what is the stagnation pressure at the inlet of the compressor. Okay, so we have intake, right? So intake, we have ambient pressure PA, and at the exit we have the stagnation pressure P01. Okay, so let me just briefly go over how intake isentropic efficiency is defined. Okay, so we have this, the ambient static pressure PA. Okay, so now let's say this is our P0A, so this is our basically Ca square by 2 Cp. Okay, so this here we will get T0A. Okay, now if since there is some flow irreversibility associated with the intake also, there will be some the stagnation pressure will not be P0A, it will be P01. Okay, let's say this is P1, this is 01, and this difference is called our C1 square by 2 Cp. Okay, right, this is again happening because our so ideally if the flow is isentropic, the stagnation pressure at the end of the intake will be equal to stagnation pressure at the intake. Okay, but again due to flow irreversibilities, remember that intake is a diffuser, so we have discussed that for isentropic flow the stagnation pressure and temperature in a diffuser will remain constant, but if the flow is non-isentropic, the stagnation temperature will remain constant, but there will be a fall in stagnation pressure. Okay, so that fall is characterized by using intake efficiency. Okay, so intake efficiency, there are two intake efficiency we can define. One is our ram efficiency, which is defined in this way: P01 by PA divided by P0A by PA. Okay, so ideally the stagnation pressure should have been to P0A, reach P0A, but it is reaching P01, so that's why the numerator is lesser than the denominator. Okay, this is one kind of intake efficiency is defined. Another is defined which is in terms of temperature differences. This is T01 prime. Okay, so T01 prime is basically this one. So here it is assumed that, so actually the stagnation temperature at the exit is, we are getting P01, but if we had to reach that pressure level isentropically, what is the temperature we will attain at the end of the intake is what is basically T01 prime divided by TA by T01 by TA. Okay, so basically this efficiency is given in the problem. Okay, so if you want to read more about this intake efficiency, if like some explanation might not be clear evidently just by listening to me, so just refer to that book that I called that Gas Turbine Theory by Saravanamutto. Okay, you can just it is explained well in that book. Okay, so you can refer to that. So this isentropic efficiency is given, so we will see that if that is the case, the stagnation pressure at the inlet to the compressor can be written in this way: 1 plus eta intake divided by Ca square by 2 Cp of air times Ta to the power gamma of air by gamma of air minus 1. Okay, so here I am adding a subscript to the specific heat Cp and also the gamma because we are doing it for air. Okay, so this is 1 plus eta of intake is 0.93, Ca is 215.67, Cp is 1005, and Ta is given as 236.2 Kelvin. Okay, gamma of air is 1.4 and Pa is given, so if you solve this we will get P01 as 0.4837 bar. Okay, so now if we go back to this, we know what is the temperature and pressure at set point 01, which is at the compressor inlet. Okay, now we know the temperature and pressure values at set point 01 and we know the compressor isentropic efficiency, and now we need to find out what and we also know the pressure ratio, that means we know P02. Okay, so P02 is Rp times P01, which is pressure ratio is 8 times 0.4837, so P02 is 3.87 bar. So this kind of problem we have done before. We have a compression process. We know the inlet temperature and pressure, the compressor isentropic efficiency, and the pressure ratio. So we have to find out what is the temperature at the exit. Okay, this kind of problem we have done before. How we do that? So we can write this compressor isentropic efficiency is our T02 S minus T01 divided by T02 minus T01, right? So T02 is T01 plus T02 prime minus T01 by eta C. So if we take T01 common, now this we can express in terms of the pressure ratio. So what we get is Rp whole to the power gamma a minus 1 by gamma a minus 1. Okay. This kind of thing we have also, if you remember, we have done before, right? So T02 will be T01 is our 259.34 plus 259.34 divided by eta C is compressor is 0.9, Rp is 8, v power 1.4 minus 1 by 1.4 minus 1. If we solve this, we will get T02 as 493.16 Kelvin. Okay, which is the answer is option B. Okay. Any questions so far? So like the thing extra that we did is to use the intake isentropic efficiency to find the pressure at the entry of the compressor, right? This part is the extra thing that we did. This what is in this slide. Okay, this on intake efficiencies, and the rest, and what we did in the next slide, this one, this is you should be familiar to this because we have done problems of this kind before. We know the pressure ratio, intake and intake temperature and intake pressure, inlet temperature and inlet pressure of at the compressor. We have to find out the exit pressure given a isentropic efficiency. Okay, any doubt, questions? Okay, thank you. Okay, so next is turbine outlet total pressure. Okay, so we find out the turbine outlet total pressure. Okay, so let me go back to the TS diagram. So I will again repeat myself. When we do this kind of thermodynamic analysis problem, the first important thing is we have to find out the temperature and pressure at each of the state points. Okay, so we know the temperature and pressure at state point 1. We have computed the temperature and pressure at state point 2. Okay, so now the question is the pressure at state point 4, right? This is the question, pressure at the total pressure at the exit of the turbine, right? So that means we have to first find out the temperature and pressure at state point 03. Okay, so temperature at state point 03 is given, which is 1180 Kelvin. Okay, so so we need to find out P04 basically, right? So T is first, we know, let's find out the things at state point 03. Okay, which is turbine inlet, right, or combustion chamber exit. So T03 is given 1180 Kelvin, this is given. Now what is P03? So in case of, if the cycle was ideal, P03 will be equal to P02, because we assume that the heat addition process is at constant pressure, but here it is not the case. So P03 equal to P02 minus the pressure loss in the combustion chamber. Okay. Now pressure loss in the combustion chamber is given as 4% of P02, right? That is what we saw. Let's go back once. So combustion pressure loss is 4% of combustion delivery pressure, okay, which is 4% of P02. So this is 0.04 times P02, which is like 0.96 of P02. So P03 will come out as 3.715 bar. Okay, now we know this. Okay, so next thing is what we need to know, what is the pressure at the end of the turbine outlet, right? Pressure at the outlet of the turbine. Okay, so first then we will do work matching between turbine and compressor. So the compressor work will be equal to the turbine work, right? Because again in aircraft engine the turbine work should be just sufficient to run the compressor. Okay, plus one thing we need to incorporate is that there is some losses due to friction in the shaft that connects the turbine rotor and the compressor rotor. So that is one thing will come, is the mechanical efficiency, right? So turbine work is slightly higher than the compressor work, and when it is multiplied with the mechanical efficiency to account for the frictional losses, that should be equal to our compressor work. Okay, so now what is the expression for work in our compressor? That is Cp of air times temperature difference, that is T02 minus T01, right? And this is equal to eta mechanical, let's say eta mech. What is the work done due to turbine? That is, here we have to take the Cp of gas, the exhaust gas, because the working fluid is exhaust gas here. Cp of exhaust gas times the temperature difference, that is T04 minus T03 minus T04. Right? Okay. This expression is clear. Now what is unknown here? T04, this is unknown, right? All the other things we know. So Cp of air is 1005, T2 is 493.16, T01 is 259.34, eta mech is 0.99, and Cp of gas is 1147, T03 is 1180, and we have to find out T04. So if we solve this, we will get T04 as 973.055 Kelvin. Okay, is this clear? Okay. This is how you do work matching between turbine and compressor. Okay, so that's why now we will see that the pressure ratio across the turbine is not the same as the pressure ratio across the compressor. Okay, but in ideal Brayton cycle we know that pressure ratio across the turbine is equal to the pressure ratio across the compressor, but that is not the case in case of aircraft engine cycle, because the pressure ratio should be just enough so that the temperature drop that we are getting produces the work output sufficient to drive the compressor. Okay, so now what we have is, if you just do the TS diagram, so this is our P03, this is our P04, 03, 04. Okay, right? Okay. So next okay, so next what we have to do is find out what is the pressure, right? So to find out the pressure P04, okay, so what we can do is you can write the definition of nozzle turbine isentropic efficiency. So that is T03 minus T04, the actual work, divided by the ideal, right? T03 minus T04s. So this is 04s, right? Okay, so now if you nozzle turbine isentropic efficiency is 0.95, T03 is 1180, T04 is 973.055, this is 1180 minus T04s, so T04s will come out as 962.16 Kelvin. Okay, so what we did here is we find out the what is the temperature if the at the end of the exit of the turbine if the process was isentropic. Okay, so now we know the temperature T03 and T at the T04s. Now we can apply the isentropic relation to find out what is the pressure level at the exit of the turbine, right? So P04 by P03 will be equal to T04s by T03 divided by gamma G by gamma G minus 1. Again, be careful, we are using the gamma for gas here. So you solve this, you will get P04 as 1.64 bar. Okay, so this is what the question asked. We have to find out the pressure at the exit of the this thing. So this what we are getting is answer option C. Okay, any doubt? Okay, good. Okay, now is the question critical nozzle pressure ratio. Okay, so this is what is said, which is known as I discussed this when I was discussing the one problem, critical temperature ratio and critical pressure ratio for nozzle. So critical pressure ratio means what is the pressure ratio if the nozzle is choking. Okay, so that is just straightforward application of that formula that I wrote, critical pressure ratio. So nozzle is between P04, that is the stagnation pressure at the exit of the nozzle, right, divided by PC. So PC is the critical pressure if the flow is sonic. Okay, so that is 1 by 1 minus 1 by eta nozzle times gamma G minus 1 by gamma G plus 1 whole to the power gamma G by gamma G minus 1. Okay, this is 1 by 1 minus 1 by eta nozzle is 0.95, gamma G is 1.33, 1.33 plus 1 whole to the power 1.33 divided by 0.33. So critical pressure ratio will come out as 1.92. Okay, so to repeat again, what is critical pressure ratio? The stagnation pressure ratio by the exit pressure ratio if the case when the flow at the exit of the nozzle is sonic, okay, or the choke. Okay, so this question, this is the what is the static temperature at the exit of the nozzle. Okay, now we know that critical pressure ratio we got as 1.92. okay, now let's say what is the pressure ratio which we are getting. Okay, so P04 now by P5. Let's see what is P04 by P5. So if we just go back to the TS diagram, sorry, yeah, so what is P5? So P5 is the static pressure at the exit of the nozzle, right? So and the nozzle is nozzle should give out the gases should exit the nozzle at the ambient pressure then, because P5 is should be equal to the ambient pressure, right? Now if we check that what is P04 by P ambient, okay, so this is P04 is 1.64 and P ambient is 0.3565. so these we get as 4.6. okay, so to expand the gases in the nozzle to ambient pressure PA, the pressure ratio we need is 4.6, but the critical pressure ratio is 1.92. what does that means is that, so at critical pressure ratio, what it means that critical pressure ratio when the nozzle gets choked, it cannot allow additional mass flow rate more than that. Okay, so but if we want to get a pressure ratio of 4, expand the gases to the ambient pressure, the pressure ratio is 4.6, but the nozzle that is available cannot allow that, the nozzle of given isentropic efficiency. Okay, so that means that the pressure ratio across the nozzle can only be maximum be 1.92. okay, which means that the P04 by P5 will be equal to 1.92. Is it clear what I am saying, or do you want me to repeat? So if the pressure, so what it means there is that if the nozzle has to expand the gases to the ambient pressure, the pressure ratio is 4.6. the maximum pressure ratio it can afford is 1.92, because that is limited by choking, because once the nozzle is choked, it cannot allow additional mass flow rate or additional pressure drop, right? So for this case the nozzle is choked, okay, and the P5 has to be equal to, so P0 by P4 will be 1.92, or P5 will be equals to 0.8553 bar. okay, so nozzle is choked and this P5 will be, the pressure ratio should be equal to this. okay, so now the nozzle exit pressure P5 is 0.8553 and the ambient pressure is 0.3565 bar. So what we can see here is the nozzle is not able to expand until the our ambient pressure. okay, So this is the nozzle exit pressure is higher than the nozzle exit pressure, sorry, the ambient pressure, right? So this is a case of under expanded case. Okay, because you can see choke nozzle, and also we can see this under expanded because the nozzle exit pressure we are getting is higher than the ambient pressure. Any questions? Clear? Not clear? Okay, good. Okay, so this is what we are getting P5. Okay, so our question is we have to find out the static temperature at the nozzle exit. Okay, so static temperature at the nozzle exit. So now we know that this is the what we have seen from there. This is the nozzle exit condition is sonic, right? Okay, so that means that at the nozzle exit the flow is sonic, which means that, or critical condition. So if you remember, we also derived a relation that when the what is the critical temperature ratio, which means that the temperature ratio, which is the stagnation temperature by static temperature at the nozzle exit when the flow is sonic, which is, which you remember, which is basically T04 by T5 is equals to gamma g plus 1 by 2. Okay, so from this we can find out what is the static temperature at the nozzle exit. So T04 is, just a second, so T04 we find out as 973.055, T5 gamma g is 1.333 plus 1 by 2, so we will get T5 as 834.17 Kelvin, which is option A. Okay, all right. Okay, so is this clear? So I guess this is the last part of the question. What is the specific thrust produced by the nozzle? Okay, right? So the specific thrust, okay, so thrust, remember we have seen there are this thrust, we know this is equal to the jet velocity, which is the exit velocity, which is here C5, minus the inlet velocity, or this is the flight speed, right? This is what we know is the expression for thrust, right? But there is another part to thrust, which is this one. Okay, so this is what we call is the pressure thrust. Okay, so this pressure thrust, so till now, if you remember the one lectures on what is the propulsive power and thrust, we have seen only this part, which is equal to the change in momentum between the inflow and the outflow, right? But there is one additional part, which is the pressure thrust. So this comes in when there is a difference between the nozzle exit pressure and the ambient pressure. So that pressure difference contributes to a thrust, and that component is equal to the nozzle exit area times that pressure difference. Okay, so now we want specific thrust, so that will be equal to C5 minus CA plus A5 by m dot times P5 minus PA. Okay, so for this we have to find out what is C5, A5 and m dot, right? CA is known, P5 is known, PA is known, right? So what is unknown is this A5 by m dot and C5. Okay, now What is C5? C5 is equal to our sonic velocity at nozzle exit condition. Because remember, this is our nozzle is choked, so at nozzle exit the Mach number is 1. So that will be equal to the speed of sound. The speed of sound is gamma g r times the temperature, gamma T5 square root of that, right? So C5 will come out as 564.91 meter per second. Okay, so P5 we have computed. Now we have to find out what is the other thing we need to find out is A5 by m dot. So let's say what is the expression for m dot. So m dot is the mass flow rate, that should be equals to the density at nozzle exit times the area at nozzle exit times the C5. But what we need to find out is A5 by m dot, which is 1 by rho 5 by C5. Okay, so now rho 5 we can find out from the equation of state, which is P5 by RT5, right? So if you use this, we will get A5 by m dot as 0.00495, and the specific thrust will be equal to C5 minus CA plus A5 by m dot P5 minus PA. So all the values we know now. If we put in everything, we will get specific thrust as 596.15 Newton per second. Newton second per kg here, which is option C. Okay, so this concludes the thermodynamic analysis of turbojet cycle. So if you have any doubts or questions in this or any other related topics discussed today, okay, so let me summarize what we final examination question pattern. I think like NPTEL share the table, right? So your questions will be online based, right? Yeah, online based. Yeah, so you will be expecting questions similar to what you have seen in the assignments only. Like, also just get used to that online calculator, because you won't be allowed physical calculators, right? So get used to that one link to online calculator is shared, right? So get used to that. So you will get questions similar to what questions similar to what is given in the assignments, like MCQ types, some numericals with options, or you might get some questions like where you have to put an integer based questions, full marks and all that. I am not sure what is the duration of the exam. Okay, all these things I won't be able to tell. So if you want to just know this, it's better you email the professors and ask them that what is the weightage on each part. But ideally, since like 50% will be from gas turbines and 50% will be from IC engines, okay, and like if it's 3 hours, maybe it's like it will be 100 marks or something. But it's better if you email the professors or put the question in the discussion forum and ask them. Okay, also maybe I will also ask the professors and let you know in the next session. So next session, so in this session I have like till now we have covered all the topics discussed in the all the 12 weeks of lectures. So in the next session what we will do is this will be a revision session. So I will try we'll solve problems like throughout the topics from all the topics from the discussed in this course, okay, and also revise some important concepts and all that we will need it for your exam, okay. Anything else? Okay, okay, thank you all for attending, and so in the again, so next week Saturday will be that will be the last problem solving session from my side. So I will try to recap the important concepts uh, discussed in this course, and also if you solve some important other devise some and solve some more problems, okay. You can bring in your doubts and whatever it is, and like if you have any specific doubt, maybe you can also like post it in a discussion forum beforehand if you like, so that I can come prepared in case I am not aware of anything at the that moment, okay. Okay, but yeah, so next session will be like that, to revise the concept and solve any other doubts that we have related to the course before your final examination, okay. Okay, then I will end today's session. Thank you all for attending. Good night and have a good weekend. Yeah, bye.